Good morning, Europe, and good evening, Numea. And I'm here today to explain you the work that I done during the last 3 years for my PhD. And I would say thank you to CNRT for the participation to the program Amiante Bonne Pratique. And during my PhD, I studied the alteration of asbestiform minerals of New Caledonia that are subjected under subtropical climate. Mineralogical monitoring and geochemistry study was carried out. There are two aims of the study, the main two aims. The first was to develop a diagnostic routinely analytical strategy able to discriminate and characterize with certainty the different species of asbestos and their capacity in the emission of fibers in mining context. And the second, to evaluate the impact of supergene alteration on the processes of genesis and emission of fibers into the environment. A focus was realized on the estimation of the role of chemical element exchange on the capacity of dispersion of fibers. So I would explain the planning for this presentation. I began with the state of art, then I done a little description of the sample of New Caledonia. The program was separated in three main subjects: the identification and characterization of mineral fibers of New Caledonia, the evaluation of the impact of supergene alteration on these processes, and the identification in situ in the mining context of mineral fibers with a portable Raman device. At the end, I conclude and I give some perspective. What is an asbestos? Asbestos is, with the term asbestos, we generally defined a commercial and regulatory term that was applied to the group of 6 minerals: the serpentine chrysotile, the amphibole actinolite, amosite, antophyllite, crocidolite, and tremolite. The 6 minerals have a specific crystal habit and several physical, chemical, and technological properties. Associated to these fibers, there are other asbestimorph fibers that can that in some cases can modulate its toxicity. This is the case, for example, of erionite and fluoroedenite. Recent studies have been dedicated to the evaluation of the potentially carcinogenic power of fibrous antigorite. We focused our attention on the study of chrysotile, tremolite, and fibrous antigorite that are present in New Caledonia, in the geological unit of New Caledonia. It should be noted that no common, non-conclusive and definitive definition of fibers, asbestos, asbestiform term are present, are available in literature. During the thesis, I mentioned the term elaborated by Nayash that replaced the term fibers with the term elongated mineral particles, including asbestiform and non-asbestiform cleavage fragments. Another important subject is that the definition of asbestos changed as a function of the scale of observation with which study as the asbestos or asbestiform of fibrous minerals. The environmental exposure to asbestiform minerals in New Caledonia is a huge health concern because naturally asbestos is present in the most part of the geological units of the New Caledonia, the ultrabasic geological units of New Caledonia. The map show the potentially, in yellow and orange, show the potentially presence of asbestiform minerals. In addition, New Caledonia is one of the most important producers of nickel from lateritic ore deposits. And in this context, mining extraction must deal with the natural occurrence of these mineral fibers. This is a typical lateritic profile that we can find in New Caledonia geological units, and we generally find chrysotile in the form of veins and veinlets embedded in the peridotite, in the altered peridotite, in the saprolite and bedrock horizon, and we generally find antigorite and tremolite mineral in the form of dike or in the shear plane, in the red and yellow limonite laterite. So under this tropical, subtropical condition, weathering processes are the main responsible for the release of fibers of the asbestos minerals. Natural deposits exposed to this condition are generally subjected to a further process of alteration. At present, a semi-quantitative method able to classify this kind of alterations is not present, it's still lacking. Conversely, geologists of mining companies develop a own system of classification of this state of alteration. I report the table for the antigrade sample, and increasing the degree of alteration from 1 to 4, we observe a greater capacity in the emission of fibers. But these criteria are all visual and morphologically. We decided to focus our attention to fibrous antigorite for different reasons. The main is that the New Caledonia legislation is the only one in the world that classifies antigorite as an asbestos. But no complete toxicology data are available at this moment. No. Recent studies realized at the Sconsetti Center have demonstrated that Caledonian antigorite is more fibrous compared to Italian or other antigorites. So the abundance of breathable fibers of antigorite in the most geological units of New Caledonia may represent an additional risk for people exposed. And in order to ensure a better risk prevention, the establishment of a powerful diagnostic analytical strategy is required. Concerning the sampling, 58 samples were collected by geologists of mining companies, Comité Interminable, 35 antigorites, tremolites, chrysotile, and 2 not identified fibers. All samples present different degree of alteration and were collected from the most important geological unit of the country. At the end scale, samples of New Caledonia show an evident lack of coherence and a very altered appearance, especially for antigorite, increasing the degree of alteration from 1 to 4. Antigorite appear more friable and characterized by a structureless aspect. Chrysotile, instead, appear in the form of little veins and veinlets, cross-cutting the serpentinous hyperidotite. And this is the typical aspect that we can find at the outcrops of New Caledonia. On the contrary, tremolite samples show a little variation in morphology as the degree of alteration increases. Tremolite is characterized by typical columnar morphology. Six analytical techniques were involved in this study, and together with the techniques recommended for a European directive, other 2 techniques, the X-ray powder diffraction and micro-Raman spectroscopy, were involved. There are 2 techniques that permit to use benchtop and portable device that can be transportable in mining context. Concerning the identification and characterization of mineral fibers of New Caledonia, mineral identification was performed by a multidisciplinary routinary approach and by a comprehensive study of texture and morphologies at different degree of alteration. In addition, polarized light microscopy associated to dispersion staining, that is a technique widely used for the analysis of fiber concentration for asbestos-containing materials, was applied to natural samples. The results show that about 60% of samples classified by mining geologists are subjected to misinterpretation. Comparing the analytical identification with the field survey, which is based on visual and morphological criteria, it's clearly evident that most of the samples have a different and more complex mineralogical nature. I report the example in the table of some specimen recognized, identified by geology of mining company as antigorite degree of alteration number 1. But we can see that the most part of sample are a melange, mixed phase antigorate chrysotile, and two samples recognized as antigorate are two samples of chrysotile. I will describe the sample 33 that is the most emblematic in this context. At the end scale, it is formally consisting of the overlapping of well-formed labelle characterized by a color by green to white. And the first preliminary X-ray powder diffraction Raman portable investigation describe that is states that is chrysotile. We decide for this reason to characterize more in detail these samples in order to better understand its real mineralogical nature. At the stereo microscope, the sample appear characterized by a lamellar morphology, but just after a mechanical stress on the surface, we observe the appearance of individual fibers. These fibers were analyzed with dispersion staining methods, and using the standard index liquid refraction at 155, we can identify the chrysotile phase. At phase contrast, we observe a beautiful pale blue with orange halo fiber. So, the observation of a petrography thin section with optical microscopy and systematic study realized with micro-Raman spectroscopy confirm the identification of chrysotile. PLM images show the typical zebra-like appearance of massive chrysotile. In addition, 60 spot analyses acquired with micro-Raman confirm that the sample was homogeneous, and we observe the typical Raman spectra of chrysotile. For this reason, we decide to go more in, to regard more the morphological nature of these samples, and the same images demonstrate the fibrous morphology of these samples. Finally, TEM associated to diffraction pattern confirm the identification of chrysotile variety. It's so interesting that chrysotile can crystallize in the form of macroscopically well-formed lamellae. For in this context, we decide to study more in detail the textural and morphological appearance of the sample of New Caledonia. Concerning chrysotile, optical microscope image show the typical characteristic image for found in literature. On the contrary, for antigorite, antigorite sample in New Caledonia consisting of randomly oriented aggregates of fibrous lamellae that show a greater type of shapes and intergrowths. We can observe in the picture 4 kinds of texture, and from left to right, star and far-formed aggregates, the most typical interpenetrating texture, lat-shaped lamella, and the fibrous blades. And all these 4 textures were found in the same sample. It means that several kinds of texture can coexist in the same sample. Concerning tremolite, no great changes in morphology were observed, and just a few samples showed height fracturation, and that is often related to a higher degree of alteration. Increasing the magnification, same images reveal the great variability in morphology of these minerals. This is an example of chrysotile that show an unusual height density of tubes, and the fragment, the particle, is formed consisting of a compact bundles of parallel fibrils. Concerning antigorite, a great variability is observed, and from a lat-shaped morphology to a more fibrous. Generally, the lamellae of antigorite show a general fibrolamellar aspect with, at the end, a fiber more curvilinear, flexible, and in this case, partial conversion into chrysotile is suggested. Comparing textural feature and morphological appearance at a different scale of observation, we can observe that several kinds of information about morphology are retained by optical microscopy. And despite its intrinsic limits related to low magnification, and that is a two-dimensional technique, the petrographic thin section retains several important information. This is true also for samples that consist of a finally, intimately intergrow of antigorite and bundles of chrysotile. It is clear in the figure on the left that there is alternance of an alternate of antigorite and chrysotile bundles and lamellae. But to verify this information, to verify this observation, we need a more degree of detail. And for this, we use the micro-Raman spectroscopy and pointing the laser beam in the different lamellae and bundles. And the Raman peaks in nitrate number region confirm this intergrowth of fibrolamellae of antigorite and the compact bundles of chrysotile. And the flexible tuft was confirmed it's chrysotile, but it's interesting to notice that a little shoulder indicated by the arrow that is at the peak position of antigorite is related to the thickness of the bundles of chrysotile. Compare the thickness of the tuft to the preparation of samples, the laser beam directly on chrysotile penetrates and is impacted by the presence of antigorite below. So, would you describe this interesting sample, the sample 18, that show a new specific and unusual texture? This is an image in a polarized light microscopy on the photography in the thin section, and we can observe an unusual star and fan-formed aggregates. This sample was identified by mine geologists as the antigorite degree of alteration number 2, and at the end scale it exhibits an unusual lamellar aspect that consists of the overlapping of dried light yellowish to pale green lamellae. Preliminary results obtained with portable Raman demonstrate that at the lower wave number we observe the typical Raman peaks spectra of antigorite. Conversely, observing the OH stretching vibration, the doublet of antigorite is shifted at higher wave numbers. This suggests the presence of the secondary and other serpentine minerals. To analyze, to study this sample by optical microscopy associated to dispersion staining, we need minimum two liquid index refractives, one for the chrysotile and one for the other variety of serpentine. For the chrysotile, we use the standard refractive index at 155.0. But for antigorite, there is not today a refractive index that was recommended by regulation, because asbestos is not except for New Caledonia context, is not considered as an asbestos. A great work of survey of different refractive index liquid was carried out, and the liquids, the refractive index value that match most closely the antigorite phase is the 156.80. We observe a fibrous lamelle characterized by a phase contrast mode of observation by a pale blue to white color, and no halo was observed. observing the dispersion staining color, observing in dark field, show that fibrolamella appear with a beautiful indigo blue color. So we test these two index values on our sample, and we observed, contrary to every expectation, that fibers exhibit an intermediate behavior and exhibit the characteristic staining color of both antigorite and chrysotile varieties. So this technique does not allow to discriminate, in this case, the serpentine species. For this reason, we decided to use the micro-Raman spectroscopy to investigate the different mineralogical assemblage on the thin petrographic section, and about 60 spot analyses have been acquired pointing the laser beam on various lamellar blades, articular particles, and at the area in contact with each other. But all 60 spot analyses are perfectly comparable, and the lower number region show the typical Raman spectra of antigorite. Conversely, the OH vibration demonstrates that all OH stretching peaks generally attributed to lizardite, antigorite, and chrysotile coexist together in the same samples to form a complex doublet. And it was the first time that I observed this complex, beautiful doublet. But even the micro-Raman study does not allow to discriminate the serpentine species. So, to investigate the morphology, some images reveal a more fibrous aspect and the appearance of flexible fiber. Is this chrysotile? Finally, TEM, associated to diffraction pattern, revealed the double nature of this sample, which consists of the intimate intergrowth of fibrous antigorite and chrysotile fibers at the micro scale. The second part of this presentation is dedicated to the evaluation of the impact of supergene alteration in the processes of genesis and emission of fibers into the environment. The impact of supergene alteration was evaluated on the antigorite and tremolite altered sample by means of X-ray powder diffraction and by scanning electron microscopy to study any modification, any possible modification on crystalline structure and on morphology. A study of the measure and trace element concentration was carried out in order to investigate the influence of weathering on chemical composition. So, two simulating chemical extraction by batch leaching experiments were performed, and a comparison of the capacity of fiber emission after leaching have been performed. As clearly evident in the slide, increasing the degree of alteration from 1 to 4 for the antigorite samples, diffraction pattern show completely comparable. No modification are observed in the peak position, in the peak broadening, or in the intensity. This is true for antigorite and for tremolite samples, and this suggests that weathering does not impact the modification in the crystalline structure. Probably this impact, weathering impact the chemical reaction at the surface. Evaluating the weathering on morphological aspects for antigorite and mixed phase antigorite and chrysotile, we observed that increasing the degree of alteration from 1 to 4, for antigorite especially, a gradual increase in porosity was observed. The space between the fibrolamellae correlated with the increase of state of alteration. In the case of antigorite and chrysotile samples, this factor was more important because probably the penetration and circulation of fluids and water between fibrils and lamellae is facilitated in the fibres of chrysotile, that's opening the structure and generate a formation and release of fibers into the environment. To test the weathering on chemical composition, analysis of major and minor elements of natural samples were carried out and here I report the data acquired for antigrade and antigrade chrysotile samples for magnesium and iron content. Compared to the data of literature that are circled in blue, Caledonian samples show systematically a lower magnesium content and an higher iron concentration. And this suggests an advanced stage of the supergene alteration also for antigrade samples that macroscopically were identified as not altered. All our samples probably are already altered. And in addition, for antigrade sample, we can observe an increase of iron content correlated with the increase of the state of alteration. So, two batch leaching experiments with MES and DTPA buffering solution extraction were carried out on not altered, classified as not altered antigrade and chrysotile samples in order to reproduce and to extract major elements. I report here the case of magnesium content, and magnesium concentration increased with time. Experiments were realized from 2 hours to 60 days, and we find a magnesium concentration higher in the Soutenance solution. This results in according with results observed on antigrade natural samples. An increase of the release of magnesium content can be seen with the increase in the degree of alteration. And it's not surprising, but extraction realized with DTPR is more important and stronger than extraction realized with MES. And this generates a more amount content of suspended particulates in the Soutenance solution. And the emission of fibers is therefore undoubtedly related to the chemical alteration of this sample. Chemical alteration induced more and participates at the processes of generate and release of fibers into the environment. The last part of the presentation is dedicated to the in situ identification, the identification in mining context of mineral fibers with the portable Raman equipment. The aim was to develop an efficient and user-friendly analytical strategy that was able to discriminate with certainty and without delay the potential asbestiform fibers from the non-armored fragments. The main contrast that we observed at the mine in front are related to climate. The temperature is very strong in New Caledonia, and the temperature is so, and the humidity is also strong. It's so difficult to use the DPI for all the time during the exposition. Several tests was performed in laboratory to test the reliability of this technique, and on 37 analyzed samples, 41 were identified without ambiguity. All these testing were realized or performed on the New Caledonian samples at a different degree of alteration. Further analyses were realized on the most altered samples in order to verify, to evaluate the goodness of data compared to the alteration. As clearly evident in the picture, despite the complete loss of cohesion of the sample, the goodness of data was not affected. A Raman, portable Raman, allowed to identify, in this case, an antigrade phase. Its work of comparing of performances of Raman portable compared to the laboratory device was realized in order to test the efficacy of this technique. And despite several intrinsic limitations related to the compact geometry of the equipment, we can conclude that observing the Raman spectra, portable equipment allow to identify all serpentine and amphibole phases. And so sorry, we Okay, no? And it's the PC. Okay, and we can use a portable Raman because the answer, the analytical answer is comparable. So finally, portable Raman was tested at the open mine of Balangero firstly, in Turin, and on 37 sample tests, for sample test, it means spot analysis, 33 allow to identify the typical mineralogical association. So, the portable Raman was tested also in New Caledonia at the open mine of Tontuta, and in this case, on 30 sample tests, 20 give a positive response, allowing to identify the mineralogical association. On overall analysis realized that 80% were successfully identified with the hand-added Raman device. To conclude, a multidisciplinary routinary approach is confirmed the only strategy possible to study and characterize fibrous serpentine and amphibole minerals. The supergene alteration does not modify the crystallinity of antigrade and tremolite, but affect the surface reaction and increase the genesis and release of fibers. It's important to remember that chrysotile can crystallize in the form of macroscopical well-formed lamellae, and the fibrous antigrade of New Caledonia displayed a great variability of texture and morphology compared to the literature. Finally, the portable Raman equipment associated to the dispersion staining observation mode should be the decisive diagnostic tool in the detection and characterization of asbestos in the mining context. For the perspective, at present, a complete mineralogical structural characterization of the serpentine and amphibole on New Caledonia is now required. And thermal analysis would have greatly improved the characterization and discrimination of altered mineral fibers of New Caledonia. Concerning the supergene alteration, further batch leaching experiments should be performed on a most exhaustive sampling, including, for example, tremolite and chrysotile. And moreover, the influence of the variation of physical chemical parameters needs to be investigated. In order to better simulate the processes of weathering at the outcrops, several cycles of hydration and dehydration should be reproduced under controlled conditions. And the variability of fiber morphology and size distribution on natural samples and on samples obtained after leaching experiments should be better investigated. Concerning the health risk in the near future, it's important to realize a detailed study of the real dispersion capacity of asbestos and fibrous minerals in the air. And actually, there is not a true understanding of the formation and emission process of these fibers, and it is important to answer to worker and population requirements. The mineralogical investigation of environmental asbestos samples coming from outcrops and or storage sites must be integrated by the complete characterization, identification and quantification of the filters collected by workers during exploitation activities. And I wish to say thank you to advisor, supervisor, prof, technician, student, PhD student, my family and friends, all people that participate with me during the last 3 years. And thank you to New Caledonia for this great experience. And thank you all for your kind attention.